So any doubt from previous lecture? So basically we discussed some examples of matrix spaces in previous lecture. So let us recall that first. So two things we discussed in the previous lecture. One thing is if we are given a basis of domain and codomain, then we can find corresponding to each linear map we can find matrix, and corresponding to each matrix m cross n matrix we can find the corresponding linear transformation if x is n dimensional and y is m dimensional. And then we discuss some examples of linear functionals. So in n dimensional it is quite clear, and we also discuss functionals over infinite dimensional vector spaces. So these are the infinite dimensional vector spaces, all four, and we discuss some examples using that. Yeah, so this map is linear because we know that if we apply f2 on x plus y, then that is nothing but x plus y derivative of that evaluated at s. And then we know that if we have two functions f and g, then f plus g dash is basically f dash plus g dash evaluated at s, and that is nothing but yeah, so here f and g are x and y basically. And then this is essentially x dash s plus y dash s, and that is f2xs plus f2ys. It preserves addition, and similarly we can check this map also preserves scalar multiplication. So this function is linear. Similarly, this instead of derivative we have integration, then integral operator is also linear. That is also linear map. And if we take a fixed S naught and a fixed point between 0 and 1, then the same maps are actually a functionals because this is a fixed number now. So we discussed some examples of matrix spaces using AMGM inequality. We derived two inequalities. First is Force inequality. Second is Minkowski inequality. For real and so this is for non-negative real numbers. So A1, B1, A1, A2, An, B1, B2, Bn are non-negative real numbers. For them, we derive two inequalities which we shall be using frequently in this course. So first instance is in showing this is a metric, we use that inequalities, right? So we define three matrices on Kn. So when K is R, Kn is basically Rn, n tuple of real numbers, and if K is C, this is n tuple of complex numbers. So over Rn or Cn, we can define three different metrics. Last one is a maximum, using maximum of the difference of coordinates modulus value, and the other two matrices, this is a Euclidean matrix, this is a addition of the coordinate matrix. So this 1, 2 and infinity matrix, we have three examples on Kn, and the same example will also extend for infinite coordinates, so that we will see today. Okay, so we have discussed all these things. So we defined three sets. First is L1. So L1 is the set of sequences x1, x2, xn, so on. So this is a sequence. So this we can also write as x1, x2, xn, so on, right? This element. But we are writing as a function of natural numbers. So why we are doing that, we will see in this lecture, right? Otherwise, these two are same thing. These two notations are same. So we are going to consider all the sequences in this set L1, which are absolutely, for which the corresponding series is absolutely convergent, right? This is meaning of the absolute convergence. So if you remember the notion of absolute convergence, if you have a series xn, so here we are writing the series xn as xj, right? j1 to infinity. This series is absolutely convergent if its modulus is, its sum is finite. It is not infinite, right? So that is meaning of absolute convergence. So L1 contains all the sequences for which the corresponding series is absolutely convergent. So what are the examples? Can you give some examples of elements of L1? So which sequences will come in L1? So basically, I'm asking the examples of absolutely convergent series. So what are the examples? You must be knowing these things. I think these are ridiculous questions.
So 1 upon n cube, 1 upon n to the power 4, etc.
Right. So basically, you are taking non-negative number series. So yeah. So these are the examples. So if you take the series 1 minus half, 1 by 3, minus 1 by 4, then this is not in L1, right? Because when we take the modulus, we get the series 1 upon n, which is divergent. And the example which you said is correct, that if we take square powers, then this will be in L1, because when we take the modulus of this series, we get 1 upon n square. So here basically we are taking j 1 to infinity, so 1 upon j square. So series is this one, but we need to take its modulus, so that is 1 upon j square, and that is convergent. So do you know what is sum of this series?
Pi square by 6.
So do you know proof of this?
Yes, sir. I know this series called Euler series, but I tried to understand this proof, but I did not able to understand whole proof on that time.
Yeah, so this is a Fourier series. We can use Fourier series to show that summation 1 upon j square is pi square by 6. Basically, we expand the function fx equals to x square using Fourier series, and the convergence of Fourier series helps here. So anyway, this is not part of the course, but the examples we are looking for in L1. What can we say about examples of L2?
We can take the series 1 upon n.
Right. So we have seen that summation 1 upon n, which is not, this series is not in L1, but that series is in L2. Because the same thing that uh, to see that this series belongs to L2, we need to, so what is the jth term here? Jth term here is xj is minus 1 upon j. So summation modulus xj square is essentially sum of summation 1 upon j square, j1 to infinity. So this is basically summation 1 upon n square series, and that is convergent. We know that. So therefore this belongs to L2. Okay, what is the example of L infinity? Okay, so we have seen that there is one element which is in L infinity, but it is not in L1. Right? So the third example is L infinity. So what are the elements of L infinity? So clearly, if we take modulus of each of these element, what will be the supremum? Supremum of 1, 1 by 2, 1 by 3, 1 by 4, so on. So supremum is 1, right? So that means that element is in L infinity. Because supremum of mod xj is basically supremum of modulus of xj is minus 1 by j, and supremum we are taking j belongs to n, and supremum of 1 by j. So basically this is the set supremum 1 by j, j belongs to n. So supremum is 1. Actually supreme, the maximum is 1, which is the element of this set. So it is actually maximum. Supremum is maximum in this example. Same way, if we take the other series also, this is also in L infinity. So here also supremum is 1. Okay, and there are simple examples also which belongs to each of these L infinity. So that is a set C00. So that is the set of all sequences x1, x2, xn, such that yeah, so there are infinitely coordinates such that xj is 0 for all j greater than some fixed number and not, right? So this sequence contains only finitely many non-zero terms. The set of sequences with only finitely many non-zero terms. So for example, if you take this set 1, 1 by 2, 1 by n, 0, 0, 0. So for some fixed n, so then this is element of this set C00, because after some fixed coordinate, all the other coordinates are 0. Right? So this set is known as the sequences which has 0 terms, all but finitely many terms are 0. Sequences with all but finitely many terms are 0. So this is an example. C00 is also example of a sequence space. So basically it is a vector space. Again, we can define coordinate wise addition and scalar multiplication here. So it is also vector space. And one more example we want to discuss, that is the sequences which converges to 0. X converges to 0. So what should we write here? X converges to 0 in K. So X is basically the, yeah, so let me write it as xn or xj converges as a sequence, it converges to 0 as n tends to infinity. So what are the sequences in C0? Again, 1 upon n sequence, it converges to 0. 1 upon n square also converges to 0. So therefore, these are the examples of element of C0. So C0 is also vector space with respect to entry-wise addition and scalar multiplication. Okay, so last time we verified some vector space. Okay, so that was given as an exercise. So let us verify today that L1 is a vector space. So, so did we define addition and scalar multiplication? No, no. So let us define. So L1 is basically the sequence is x1, x2, then so on, such that the series is corresponding series is absolutely convergent. So if we have two sequences which belongs to L1, then we want to define the scalar, the addition and scalar multiplication. So let x1, x2, xn, and These are two elements of L1. So we define the vector addition as, so we are defining x plus y is equals to entry wise addition. So that means first entry addition, that is first coordinate, second coordinate is second entry addition, and so on. So we are defining this way, but we should check that x plus y also should be in L1, right? So that we can do because since x and y is in L1, we have x and y both is a absolutely convergent series. So therefore what we get? Therefore we get, we take the summation 1 to, let us say k, then what we get, xj plus yj, we can write as, this is less than or equals to, we can use triangular inequality. So we get this is xj plus summation yj. And then we know that this is a sum of non-negative numbers, and if we take k tends to infinity here, then we get this is less than equals to the limit of this. So what I'm saying is that this is a partial sum of this series, right? So this is a partial sum of this series. Similarly, this is a series of non-negative numbers, so it must be less than or equals to j1 to infinity yj. Right, so this is we know because, for example, if we take the series 1 upon 1 plus 1 by 2 plus 1 by 3 up to 1 by n, let us say square, and this is always less than equals to the whole series, right? These are only finitely many terms, these are all the terms of the series. That is what we are using, that these finite terms are less than equals to infinite terms if the series is convergent. So basically we are using the series is of non-negative terms, and it is convergent also. So now this is a fixed number because this series is convergent, and this is also fixed number because the other series is also convergent. So this sum of fixed number is, this is a fixed some real number which is other than infinity, and this series is a series of non-negative numbers which is bounded by this fixed number. So what can we say about this series, whether it is convergent? So do you remember any result of real analysis that if xn is a bounded sequence of non-negative real numbers, uh, bounded means yeah, bounded monotonic, then it converges. So do you remember this result?
Yes, sir.
Right? And then we know that every series is a limit of partial sum of the series. Right? So this is a partial sum. So we have shown that this partial sum. So what is this partial sum? Partial sum is corresponding to this sequence, right? So addition sequence. So since partial sum, which is a sequence of non-negative number that is bounded, so therefore the sequence converges. So these two things basically we are using here. Okay, so this is regarding that whenever we have what we have shown that x plus y is also in L1 because we use x and y belongs to L1. So these two series are converges, and therefore we have shown that this series is converges, and this series is corresponding to the sequence x plus y, this one, because we are using coordinate of that. So let's write down that finally, therefore x plus y belongs to L1. Okay. Similarly, so since x plus y belongs to L1, we can define the vector space addition. Right. So we have checked that this is element of L1. So addition we have defined over the elements of L1. Now let us define the scalar product. Similarly, for k belongs to k, we define the scalar product by k times x, which is k x1, x2, so on. Yeah, so basically, what is k times this? So we need to multiply k inside. So this is the definition of scalar product of k with element of L1. So we need to check that whether this is in L2, which this is in L1 or not. This is in L1 because again we are going to use that x belongs to L1. That means summation xj is modulus xj is convergent. So therefore summation modulus k xj, that is the series corresponding to this element, so that we can write as summation mod k mod xj, and since summation mod xj series is convergent, we can take modulus k outside, and this is convergent. So therefore, since this element is in L1, we can define the scalar product. So addition and scalar product we can define. The other properties are other properties of vector space is easy to verify. For L1. Okay, so for example, what is the zero element? So zero element is all the elements of the sequence is zero. So that is also in L1, because if we add all these coordinates, modulus of all these coordinates, it is zero. So therefore, it is in L1. On the other hand, if x is x1, x2, xn, right? If this is in L1, then what can we say about the negative element of this? So to show it is a vector space, we need to find the negative element.
Sir, can we prove the property of subspace to prove that this is a vector space? That
Yeah,
alpha
but
x plus beta y belongs to V.
for that you need to give me some vector space.
Sir, we can form a vector space of all sequences by pointwise addition.
Pointwise addition.
Then L1 will be a subspace of the given vector space because we are taking again sequence which are convergent.
So you are taking convergent sequences.
No, sir, I am taking vector space of all sequences by pointwise addition, and L1 is a subspace of all those sequences whose SOPS is convergent.
Yeah, that can be done actually. So what you are saying is that so which side you are saying? Let us verify whether it is a vector space or not. So you take, for example, let us take X. X is the set of all sequences of entries from K. Yeah, so that is basically the sequence X is equals to X1, X2, Xk, and so on, such that each Xk belongs to K. So let's call it J. And then we are defining X plus YY. So here Y we are taking as Y1, Y2, Yj, and so on belongs to X. So X plus Y is X1, Y1, X1 plus Y1, X2 plus Y2, and so on. So clearly this is also a sequence, so this belongs to X, and scalar multiplication also we can define, that is AX1, AX2, and so on. Yeah, so this is a vector space, that is correct. So this you can check other properties easily and conclude that X is a vector space. Okay, so what is the zero element? We already observed that 0, 0, 0 is a zero element. What is the negative element of x? It should be minus x1, minus x2, and so on. Right. So this is the negative element of this. So that if we add this sequence plus this sequence, we get the zero sequence. Okay. So these are the operation, and then we can, as you have mentioned, we can see easily that this is a subspace. So essentially, we already checked that it is a subspace because we take two elements. It is element of L1, and it also preserves the scalar multiplication. Uh, yeah. So it satisfies both the property of subspace. So L1 is a subspace. Similarly, we can check L2 and L infinity are subspaces of X. Okay, so this is regarding this is a vector space. Now the next question is, can we define metric over this vector space? So in the previous lecture, we defined different metrics. One metric that was, yeah. So if we have two sequences x and y, then we can define d1 xy. That is the first one metric, two metric, and infinity metric that was using maximum. But here we have n coordinates. But now we have infinitely many coordinates. But still we can define these maps. So let us define what are these functions. So define first function is d1 of xy, that is defined to be summation j1 to infinity xj minus yj. So this we are defining for x and y is in L1. So first thing we need to check is that this is a real number, right? So we cannot define directly that d1 xy is this. You recall the definition, then every metric is a function from x to x plus x to r. So that means this should be real number. Real number means it should be convergent. The series should be convergent. It cannot be infinite. Otherwise, it is not a real number. So second metric we define, that is summation j1 to infinity modulus xj minus yj square. So that we are defining for elements of L2. And the third metric which we shall define, that is summation. Instead of summation we have supremum. So here infinity matrix was defined using maximum, but now we have infinite coordinates. So we are defining as supremum of x1 minus x, 1 minus x, 1 minus x, y, 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 1 minus x x2 minus y2 and so on. Again, here we need to check this is a finite number. So supremum is not infinite, that we need to check. So here we have the elements of infinity, L infinity. So let us check these properties. So to check the first property, what is given is we are given two elements of L1. So let x and y. So x is x1, x2, xn. In L1, y is also y1, y2, so on in L1. So that means what? That means we know that this corresponding series is absolutely convergent. And we want to show that this series is convergent, basically using this convergence of these two absolute convergent. So if you want to use this series and show that this is convergent, so how we'll show that? Any idea? We know that summation modulus xj is convergent, summation modulus yj is convergent, and we want to show that summation modulus xj minus yj is convergent. So what we will do here, we can use triangular inequality. So this term is less than equals to modulus xj plus modulus yj for all j, right? And then we know that this is less than equals to summation modulus xj. The second term is less than equals to summation mod yj, right? And that means this term is less than equals to these fixed numbers, right? So if you take summation, again this is a monotonically increasing bounded above sequence. So first we can actually take the summation over finitely many terms. So let's say 1 to k. So then this is less than equals to 1 to k, 1 to k. So basically we are comparing the partial sum, and then we can take limit k tends to infinity. So now this is a sequence of partial sum bounded above with the non-negative terms. So this is convergent. Okay, so that means this is convergent, and so that means d1 of xy is a finite real number. So d1 function we can define, and once we can define d1 function, the next thing to verify is it is a metric. So metric, there are three properties. symmetric is very simple, just because we know that modulus of xj minus yj is equals to modulus of yj minus xj. So that means d1 of xy is d1 of yx, and we can see that this is a d1 of xx is 0, and d1 of xy is always non-negative, right? And d1 of xy is 0, that means it is x is exactly y, right? That is also clear because d1 of xy is 0, that implies summation this is 0, right? And if this is 0, then each coordinate is 0. So that will give us xj is equals to yj, and that means x equals to 1. So distance d of xy, d1 of xy is 0, that means x is equals to y, and if x equals to y, then d1 of xy is 0, right? And last property, triangular inequality, we need to check for d1 metric. So for triangle inequality, what we have is xj minus yj. We know that this is less than equals to always xj minus some other sequence z plus zj minus yj. So we are basically taking a new sequence, z is equals to z1, z2, zn, and l1. So x and y already is in l1. We are taking third sequence z. With respect to z sequence, this xj, yj, zj are entry of the sequence. So they are real or complex number. And for that we have triangular inequality for each j. Right. And then now we know that now we can take the partial sum and then take the limit of the partial sum. So we get summation 1 to infinity zj. So this all three series are convergent because of this distance is finite. So finally, what is this? This is d1 of x with y less than equals to d1 of x with z, d1 of z with y. So therefore, triangular inequality for d1 holds. So similarly, we can. So finally, what we have verified, therefore, d1 is a matrix on L1. So similarly, we can check that D infinity is a matrix on L infinity. So some of the things I'm saying similarly we can verify. Those things I'm leaving as an exercise, so you are supposed to do those things. There may be some questions in exams from that. Right. So for example, here I am leaving that D infinity is a matrix on L infinity. In exam, I can ask that why it is so. So just verify that the proof is very similar, but the metric is different. Here the metric is summation, but here matrix is in terms of supplement. But more or less the proof is having same idea. So I'm leaving on that. So last, let us verify that L2 satisfies triangular inequality. Verify that D2 satisfies triangle inequality for L2. So to check, because other property D2 satisfies very trivially, so that is also easy to verify. Symmetry and all that, only this property we need to check. So let us start with three elements. X is equals to x1, x2, xn is element of L2. Y is equals to y1, y2, yn, and z is equals to z1, z2, zn. These three are elements of L2 that is given. So that means what? That means summation xj square. This series is convergent. This series is convergent, and the third series also convergent. Okay, and then we discuss some inequalities. What is that? Cauchy-Schwarz inequality and Minkowski inequality. So what does the Minkowski inequality says? Minkowski inequality says that if this series is convergent, this series is convergent, then the addition is convergent. Right. So that will give us that. Therefore, summation j1 to k xj minus yj square. So what can we say about this series? Whether it is convergent? So we can rewrite this series as so if you want to apply this criteria, then we need to write this series as modulus xj plus modulus yj square, right? Because this thing is less than or equals to this. So now we can apply Minkowski inequality, and that will give us this term is less than or equals to right. I think square root is up to this only. So basically we are taking its square root. So now we can apply this one, square root of this is less than or equals to this, and then we know that this is convergent series, so this is less than or equals to summation 1 to infinity xj square 1 to infinity yj square. So this is convergent means this is a fixed number. So this series is bounded by some positive number. So now this is a monotonic, this is a partial sum of a series which is series of uh, which is a sequence of non-negative real number, and it is bounded above by fixed number. So therefore, it's this series itself is convergent. So what we have shown is that whenever x and y belongs to L2, the sequence x minus y also belongs to L2. Or in other words, two distance of x and y is in L2. This is two distance of x and y, d2xy. Okay, so for triangular inequality, we start with the left side, that is square root of, just a minute. Yeah, so square root of summation 1 to n. So what we want to show, we want to show basically d2 of xy is less than or equals to, for triangular inequality, we show that this is less than or equals to 2 distance of xz plus d2 of zy. So now this means we need to show that square root of summation 1 to infinity. So that is what I define as d2, right? No, I forgot to write square root here. So that is square root of this. Okay, so it is same as Euclidean distance. So xj minus yj square, which is less than or equals to square root of summation xj minus zj square plus square root of zj minus yj square. So this thing we need to show. To prove this, whenever we want to prove any result related to series, we need to consider the partial sum, nth partial sum. So first let us show this for the nth partial sum, then we'll take the limit so that we'll get the result for the series. So let us start with the nth partial sum of the left series. So that is in terms of x minus y. Summation 1 to n modulus xj minus yj square. If you take its square root, then we can write that this term is less than or equals to summation 1 to n. This term we can use triangle inequality of real or complex number. So that we can write as xj minus zj plus zj minus yj. Right. So modulus xj minus yj is less than or equals to this term. So therefore its square is less than or equals to this square. And then we can take summation and square root both the side. So we get this term, and then we can again use Minkowski inequality, right? Because we have two non-negative numbers. So these two are non-negative numbers, aj, bj. When we apply Minkowski inequality, we get this is less than equals to square root of summation 1 to n aj square just a minute. So we get aj square plus, so that should be z here, right? Okay, so so this is what we have, and then we know that this right hand side terms, these are basically the nth partial sums of the series summation modulus xj minus zj and summation modulus zj minus yj square, right? So that means this is less than equals to square root of plus square root of, so every time I'm writing y, but this is z. Okay. So these two series are convergent. So therefore we can write this is less than equals to this. So now what is this? This is this two distance of x and z plus two distance of z and y. Right, so what we have shown is that nth partial sum of the first series is less than or equals to these fixed numbers. Again, it is a sequence and sequence of nth partial sum, which is non-negative term sequence, which is bounded above by fixed numbers. So take n tends to infinity, we get square root of summation j1 to infinity xj minus yj square is less than or equals to d2xz plus d2z1, and the left side is nothing but d2 of xy. So we have verified the triangular inequality for the L2 space. Other properties of uh, can be verified easily to conclude that d2 is a metric on L2. So these are the three examples. D2 is metric on L2, L infinity, D infinity is metric on L infinity, and D1 is metric on L1. So L1, L2, and L infinity are metric spaces. So one last example which we want to discuss is the supremum metric we can also define on functions, on the bounded functions. So let T be a non-empty set over any non-empty set. We can define a function x from T to K. So this is a scalar valued function is called bounded. So bounded on the entire domain if there exists some bound such that modulus xt is less than or equals to this particular number for all t in T. So this capital T is a fixed set. Right, this is the usual definition of function which is bounded. So we denote a set of all bounded scalar valued functions functions by B of T. So B of T is the set of all bounded functions And we can easily check that it is a vector space. So if we take two functions x and y, x is bounded by alpha, y is bounded by beta, then x plus y we can show that it is bounded by alpha plus beta. So essentially x plus y is also a bounded function, right? So we are taking pointwise addition of the function, and same way we can define pointwise scalar multiplication. So we can easily check that the set of all bounded functions it is a vector space. Clearly, Bt is a linear space with respect to pointwise addition and scalar multiplication. So it is a vector space, and moreover, this vector space we can define metric over this. So if we take any two elements for x and y in Vt, that is a bounded function on T, we define sup matrix, so infinity matrix of x and y. It is defined as supremum of modulus of xt minus yt. But T is element of the set capital T. So again, it is very easy to check that the infinity is a metric on Bt. So this metric is, its name is sup metric because it is defined using supremum, right? And in particular, it generalize L infinity set. In particular, if you take capital T to be the set of natural numbers, then Bt is nothing but L infinity, right? Because if you take T is equals to set of natural numbers, then X is a function defined on natural numbers. That means it is a sequence, right? And bounded function definition is same as bounded sequence. So if sequence is bounded, we can find the supremum. That is exactly this thing. So whenever we have a matrix space, we can define the convergence of sequence in a matrix space. So the sequence xn of the elements of the matrix space xd. So X is a matrix space with matrix D. If we take sequence of elements of that matrix space, we say that it converges to element X of capital X if, what is the definition of sequence convergence in matrix space? Do you remember? I think you studied that in analysis one, right?
Yes, sir. For every epsilon greater than 0, we have an minus x is less than epsilon. For all,
Not minus, basically it is a distance now.
yes, sir, distance.
So xn with x is less than epsilon. Yeah, so there exists n0. fixed number, natural number, such that this distance is less than epsilon for all n greater than equals to n0. Right. So this is definition of convergence of sequence in matrix space. So question is that what this definition reduces corresponding to the matrix d1, d2 and dn in LP spaces. So let we take P to be 1, 2 or infinity, and we are defining the set X to be LP. So when P is 1, it is L1, P is 2, it is L2, P is infinity, it is L infinity, and we have the metric also accordingly. So metric is dp. So that we denote as d1, d2 and d infinity, depending on P is 1, 2 or infinity. Then we say that xn, which is a sequence in L1, it converges to x in L1, means, so basically when we consider L1, we will consider the D1 metric. So this means this sequence converges to x in D1 matrix, right, as n tends to infinity. And that D1 metric, we know that D1 metric is summation j1 to infinity the function evaluated at j minus second function evaluated at j modulus of that, it converges to 0 as n tends to infinity. So now you can see that we are considering the sequence of sequence, right? Because every element of L1 is a sequence, and we are taking the sequence of elements of sequence. Therefore, this notation we are using, the bracket J notation. Okay, so this is the condition which is required for the convergence of sequence in L1. Similarly, if we have a sequence xn of elements of L2, that means the corresponding series summation xn j square is convergent. Modulus of xn j square is convergent. So this means in two matrix xn with x converges to 0, and that means summation xnj minus xj square goes to 0 as n tends to infinity. So this is two distance, two matrix, and last one is xn converges to x in L infinity, means in the soup matrix xn minus x goes to 0 as n tends to infinity. So that is basically supremum of xnj minus xj. This goes to 0 as n tends to infinity. So now any sequence converges in sup norm. That means by definition, what does this means? This means that for every epsilon greater than 0, there exists n naught belongs to n, such that supremum of xnj minus xj is less than epsilon for all n greater than equals to n naught. And this means so this is true for every j, right? Because it converges for supremum, so that means xn minus xj less than epsilon for all j belongs to n, and for all n greater than equals to n naught. So if some function satisfies this property for every coordinate, so then what can we say about convergence of such function? We call it a uniform convergence, right? So I believe you studied uniform convergence in analysis 1, right? So if this and not does not depend on j, then the convergence is essentially uniform convergence. Okay, so let me stop here. This is enough for today.